So I want to compute the variance of the sample mean for this population of size 4 for this coin toss experiment. So I'm just using the formula. What is the formula? Take all possible values of the sample mean, subtract from it the expectation value of the sample mean, which is mu, which is the population mean, square it, multiply it with the probability of getting this particular sample mean. Variation of the sample mean. So I have all the data in front of me. One possible value is that you have 1 minus half. This is 1 and this is half. You square it and you see, look up what is the probability of 1. It is 1 by 16. You add to it the next value, which is 3 by 4. 3 by 4 minus half square, and look up what is the probability. It's 1 by 4. The next is half. Half minus half, this is not going to even contribute, but let's just write its probability is 3 by 8. And then you have 1 by 4 minus half. This is the value of the mean, and this is the expectation value of the sample mean. And its probability is 1 by 4. And then you have this last number 0 minus half, and its probability is 1 by 16. So if you compute it, this is just 1 by 4 times 1 by 16. This is coming from here. Then this guy gives you 3 minus 1 by 4 square. So you have a 3 by 4 and minus 2 by 4. Half I can write as 2 by 4. So it's going to give me 3 minus 2, 1 by 4 square. This is 0. This gives me, again, I have minus 1 by 4 square times 1 by 4. And this guy gives me minus 1 by 2 square, which is half 1 by 4 times 1 by 16. So what do I get? I get 1 by 16, over here 1 by 16, over here 1 by 16, and they are all being multiplied by 1 by 4. So I have 4 1 by 16s. Uh, 4 times 1 over 4, 1 by 16. So it is equal to 1 by 16. And when I take the square root, that gives me 1 by 4 for the sigma. So what I have got, this has been further reduced. It has become 0.25. This is the standard deviation of the standard mean. And I expect it to be equal to sigma over under root times the population size, Original sigma was 1/2. Population size is 4. And I have this exactly equal to this thing. I have verified this formula. So this formula works. And in fact, I can say something more. There's some more hint in this probability distribution in this particular sample. And notice that over here, I didn't need to include any finite size correction because the population is, in this case, infinite. So the formula works perfectly well. So any question? Any question?
So can you scroll down?
You can do this calculation. The important thing is this line. How did we get this? Got it from this data, which we got by listing all the possible samples. These probabilities are just relative frequencies in the random samples. Now, in this case, because everything is known about this problem, we know the population probability density exactly. Well, that I computed up here, the population mean. See over here. Just using the formula that tail, which is given value 0, has a probability half. Head, which is given a value 1, has a probability half. So the population mean is half. It's just so intuitive. If the tail is 0, head is half, where is the mean? Because they are both equally likely. Because they are equally likely, the mean is exactly in between them at half. Now, in this case, because everything is known about the population density, and these are just examples to develop these ideas, I could construct the probability distribution of this sample of size 4. And for the sample of size 4, I found out that I have 5 different values of sample means. What I'm drawing over here are sample means. And over here are probabilities. That if I pick a random sample, what is the probability that the mean of that sample would be 3/4 or half or 1/4 or 0? So that's plotted in this graph. In this is called a histogram. But if I try to replace it by a curve, kind of draw a curve through them, looks like a very interesting kind of curve, kind of a bell shape. And it turns out that this bell-shaped curve is extremely important. I suppose that you have studied about it in the last course, but I'm going to review it a little bit in a little bit more detail than probably is needed. So this bell-shaped curve, it appears again and again. And we will see that it's no coincidence that in this case we got the bell-shaped curve. In fact, whenever you draw some samples from a population, if the sample size is big enough, if it's not a very small sample, then the population mean, their probability density is always almost given by this kind of a bell shape, which is called a normal curve. Normal probability distribution. So this is actually a theorem. We won't prove this theorem, but we will use it a lot. So it's very, very important. This is called the central limit theorem. It says no matter what is the distribution of the population, like in this case, the population distribution wasn't bell-shaped. That was kind of a square. Each was equally likely. No matter what is the distribution of the population, for a large enough sample size, the probability distribution of the population of the sample mean of sample means is normal, is this bell shape. So to understand this theorem correctly and to use it correctly, we need to first understand that what is a normal curve, a normal normal probability distribution. So I want to study normal probability distribution. Intuitively, it's clear it's this kind of a bell shape which you create, but to understand it more thoroughly, let's go in steps. I will start by just talking about a kind of a function. So, and just to differentiate some closely related functions, I'll start with some other name, although some people just call every one of them as Gaussian or a normal curve. So let's consider a Gaussian curve. What's a curve? It's just some function. You have plotted a function. You have, let's call this Gaussian as g of x. You give values to x. You will get values for g of x and you will get some curve. So what is the g of x I am considering? This is not Gaussian. Gauss did so much in mathematics that almost everything has a Gaussian in its name. So what is this function which I am defining? I'll just go, because finally I'll define a very specific function which I will call the normal curve. So I'm just right now trying to build up to that. So I'm just considering it to be like this. Now, what does this kind of a function? I'll try to plot it. So let me not start with this figure. So what kind of function is this? Well, first of all, if I put x equal to 0, this is just e to the power 0. So anything power 0 is 1. So at this point, this is at 1. And also, when I go towards positive powers of x, it has a minus sign over here. So it's a decreasing exponential. As values of x increase, this decrease as a power of e. So it decreases very, very fast. But also, since it's a square over x, if I give it negative values of x, the square again makes them positive. So again, it decreases. The value on the y-axis, the values of g of x I'm plotting on the y-axis, they again start decreasing very quickly. So this kind of a function takes the form of a bell which is very, very quickly decreasing. And if I give x a value a, what happens to this function? Well, let's not give it a, let's give it 1 over under root a. At x is equal to 1 over under root a, let's call it this value x naught. Oh, let's just say. What do I get? I get e minus a, 1 over a, so 1 over e. And e, you know, is this number. And 1 over e gives you something like 0.37 something. Now, what happens if so by the time I'm over here at x is equal to 1 over under root a, or on this side, doesn't matter if you give it plus value or negative, it's symmetric around this axis. On both sides, it takes same value. Whatever value is at x is equal to a or x is equal to b, the same value you get on the y-axis for x is equal to minus b. Because there's a square over x. It's a symmetric, or what you call an even function. So suppose, so at x is equal to 1 over under root a, it has already reduced to about 0.37 from its top value. Top value is 1. It doesn't take values more than 1. Suppose I try to move a little bit more. I double the distance. I go to the double this distance. What happens to this function then? This is going to be e to the minus a 4 over a to the e to the minus 4, which is actually very, very small. It's 0.018. And if I double the distance again, I go to the 3a, it would be e to the minus 9, which is extremely small. So all it tells you is that once you have crossed this point, where, so this value, this a, which was appearing in this function, this controls that when it will start decreasing very, very fast. Once you cross this, then it decreases very, very quickly. This is called an exponential decrease. So it's exponential decreasing on both sides, and it's only appreciable within a small range, which you can look up by looking at that what is the coefficient of x square. So it could be like e to the minus 3x square, e to the minus 4x square. This coefficient tells you that until how long it has some appreciable values, and beyond that it will be dropping very, very quickly. So I think we are running out of time, so let's stop here and we will continue from here day after tomorrow. Any question?
So is there any book that I could like refer to for this topic?
Yeah, the book is New Bolt, is written, is mentioned in the syllabus. If you go to LMS,
can we add you to the WhatsApp group?
Don't you have access to LMS?
No, we do have it, but like it's better if we can like talk to you if we could, if you face any problem.
We have a WhatsApp group.
Yeah, so we could just add you on it.
Okay.
Okay, you can add me on it, but don't expect me to read all the messages because all these kind of groups are totally spammed.
Yeah, no worries, sir. But like it'll be official if we get into it.
Okay, you can add me there, but I can't promise that I'll, especially if it gets spammed, then don't expect me to read all of that.
Could you share your number, please?
Okay, my number is, let me write here. I think it got only to you. Whoever Muhammad Shazil is. Were you Shazil who was just talking to me?
No, sir. I'm
No,
Ahmed.
sir, it was
Okay,
Shazil.
let me send it to the group. How do I do it? Why does it go to...
Sir, I can forward it.
Yeah, can you post it here? I don't know how to, why my messages are going to Muhammad Shazil. I don't know. Okay, now I know. Wait,
Sir, I can do
yeah.
Thank you, sir.
that. सर आपने भी यहाँ कहा था कि 0.37 जब आएगा तो 1 पे एकदम से एक्सपोनेंशियली डिक्रीज होगा तो
I
इसका क्या
I
मतलब है?
can barely hear you.
So you said कि 0.37 जब वैल्यू निकली थी तो एकदम से एक्सपोनेंशियली डिक्रीज होगा ग्राफ पे
Hmm.
बीच में तो उसका क्या मतलब है सर?
Well, it's exponentially decreasing all the way. It's just I'm just saying you can, by looking at this number, which is in front of your variable x, you can tell कि किस range के अंदर इसकी कोई appreciable value होगी. Like beyond that, it's if you double this value, well, actually it comes like this. If you double this value, you have decreased the function by a huge amount. It's like 0.018 of the original value is only left. So this variable here, this tells you how broad this function is. So exponentials, they decrease very, very quickly. But when you are starting up, you may not realize that at some point it will decrease very, very quickly. Because everything which starts, it starts at a certain rate. Only when you cross this value, you start realizing, because you have covered, let's say if this is a distance of 1 meter, if it's a distance scale, you have covered a distance of 1 meter, you were expecting that this thing is slowly going down. In 1 meter, I have gone down by 0.37, or let's say in 1 second. But in the next second, you have gone down by a huge amount. You have only left 0.018. And in the next second, even more at an exponential rate. So that's the point, that this parameter over here, it controls that how fast it's decreasing. That at what point its exponential behavior becomes apparent.
Right.
So any other question? If not, I'm gonna just end it here.
Thank you, sir.